Shouldn't be that afraid of it or what's the word I'm looking for? Intimidated by something like this. If you're not intimidated by a 2-3 zone forced air system, you're confident you can transfer the BTUs for heating and cooling a home. Let's get you confident so you can transfer BTUs with boilers, right? Because it's about the same. But what we do with hydronics, we deliver a better heating system, the most efficient, the most comfortable type of heat, okay? So in a home, it's gonna be the most comfortable experience you have. And as a homeowner, and you're paying the bill, and you're comfortable, and it's efficient, you're gonna rave about this system to all of your friends, to your family members, right? If it works really good and you're super comfortable, you're happy with it, just like anything in life, you're going to talk about that, share that with people you love, people that you run into, right? That's how hydronics spreads, because it is more expensive to do a hydronic system, but once you've experienced it, you have to have it if it's been done right. Now, this industry has struggled with folks doing it half-assed, okay? And somebody pays top dollar for a system, and they don't get what they bargained for, what they paid for, right? The system works, but not when it gets cold, super cold. That doesn't work, okay? That's a swing and a miss. So what we're here to do is kind of drive that home, like a working system, a good working system is going to get you more jobs. It's going to, it's just going to help spread this heating type of system, or this type of heating system, to more builders, to more homeowners. They can get good systems that work even when it gets cold out. So that's what we're here to really try to help you guys with today. So you got the clicker engage on this. So, Mike, it looks like the majority of it's just going to be what we're set up to do.
Okay.
We got one guy requesting, more on the pressure type stuff. So
We'll get into that probably with the Thompson.
great.
Yeah. I'm good. Yeah, we're good, Mike.
So,
Question back here.
yeah.
Hey, Mike, so can you guys touch on maybe like inhibitors and stuff too?
Yes, absolutely.
Okay,
Water quality
thank you.
is very important, and we'll talk about that for sure. So, John Stone, we're bringers of knowledge and all the parts you'll ever need, right? We got 4 locations: Oak Creek, our new one here in Milwaukee, Fond du Lac, and Waukesha. So if you need to know where we're at. We also have the addresses and numbers on their notepads there. This is part of our training lab in Fond du Lac. It was an early picture as we're progressing in there. So we have 2 live fire boilers in there. We have 2 live fire boilers here. So today we're going to talk about gravity systems. I need to be able to see my screen, otherwise I'll be looking backwards. So gravity systems: single pipe, two pipe reverse return, primary, secondary piping systems. These are all kinds of systems that you guys are going to run into out in the field. Some more common than others, but when you do run into them, we want you to understand what you're looking at, okay? In those systems, we're going to discuss some of the key components that you have in that system that really is the magic behind making it work, okay? We'll take a quick break because you guys will get tired of hearing us talk, at least for a little bit. and need to go use the restroom. If you have to take a phone call, by all means, we're not here to stop you from doing that, but please just take it out to the foyer there. What else are we gonna talk about? We're gonna talk about the universal hydronics formula. And that's that math that I was talking about, the magic behind how we figure all this stuff out. And that's basically a simple equation that we also have apps for that can help us do these problem-solving exercises. That's gonna be that B&G Sizer. That's one of the main ones we talk about, B&G System Sizer. In all of our classes, we discuss downloading that app onto your smart device, tablet. In the years past, some, what was it, the Samsung or the Galaxy phones wouldn't download that, but now it does, and I think it's better than the Apple app, so we'll talk about that, and we'll use it to go over exercises, problem solving. We'll go through that app, talk about that. What else? We'll go over a little bit about servicing. Nobody here discuss like service issues. What do we do with service? It's gonna be brief. We'll discuss some of that and some troubleshooting things with boilers at the end of this. So, any questions so far? All right. Well, first system kind of is an archaic one, older, bigger homes. You'll see this open gravity system. Now, that first word is open. That means the system's open to the atmosphere. Now, in this little rudimentary drawing here, this is the expansion tank right here. Now, fellas, this isn't down in the boiler room, as you can tell. You see, that's gonna be mounted over the top of the highest radiation in the system. And some guys may go in and say, oh, that's a steam boiler, because you don't see a pump. There's no circulator or pump on this system. The piping is going to be usually dramatically oversized, like 3 to maybe 6 inch even I've seen in some houses. Making it very, very slow to react, right? These systems are out there, they're still working, but one of the biggest problems is there's no zoning on this thing. They're just waiting for this big tub of water here to heat up and for that heat to start to migrate. How many here believe heat rises? Okay, majority of my class. So, I'm here to debunk that rumor, okay? Heat doesn't rise. Heat goes to cold, okay? Just like high pressure goes to low pressure. If I teach you 2 things, that's the 2 things I expect you to take out of my class. Hot goes to cold. It doesn't have to be going up. Do we feel heat from the sun? When it comes out here in Wisconsin, we do. So what we got to understand is that's what's happening. All of this pipe, all of the mass of the pipe, all of the water volume in the system is going to gradually start to migrate to the cold spots in the system. So it takes a while. It's going to be a long cycle for this thing when it kicks on a cold start. So it's waiting for all of this system to get hot. Now the thermostat's up here on the middle level. Now there could be a fight on where this thing lands, right? Who gets the control? Is it this floor? Is it this floor? That's, there's a big issue there with transferring that heat, because it's just, once this thing starts, it's gonna get hot and it's gonna stay hot. So these type of systems were generally coal fed, right? They just stoke that fire, it stays burning all night, we don't have to worry about on and off cycles, it just stays hot. Just like a lot of old steam systems were designed to be coal fed, they were burning all night long. You never had that flame go out. You never had the need for all these vacuum breakers and air bleeders and all this stuff on a steam system, but now we've got burners that go on and off, and that system gets cold. So, but anyway, that's how it was designed. Not that good, right? Everybody agree? We wouldn't do a new system with gigantic pipes, no pump on it, and, yeah, you got a question?
As an example of open system, I don't think it's a gravity system, but like the modern wood boilers that people put in their backyards,
Yep.
they do have pumps.
Some of them are open, some of them are closed pressurized, so you just gotta know what you're getting a hold of.
And typically, when you're dealing with an open system like that, ideally, in my opinion, ideally, it's best to separate that system out with a plate-to-plate heat exchanger.
Right.
Because almost all the time, you're gonna have a backup heat source, because the homeowner may not stoke that wood boiler. So typically, what you're gonna do is you're gonna pressurize that, or you're gonna have that open system on one side of the brazed plate heat exchanger, then you'll have, natural gas burning boiler on the other side of that heat exchanger, just in case you don't have hot water coming from that wood boiler, right? So we do like to separate that open system from the closed system. If you left it open the whole way through, you'd have to change a lot of the different system components out. You'd have to have a non-ferrous metal pump housing, so you'd have to have bronze or stainless steel pumps. That gets to be a bit expensive. Having air in a hydronic system is we'll discuss later, it becomes very problematic as well. So separating that out, eliminating, that air through air eliminators is gonna be crucial, so.
Any questions on the gravity style? Anybody running into these? Yeah?
Yeah, I got a 1929 Lowell McLean, that's still running.
Still running?
Yeah.
You got the doors on the front still?
Well, they converted it to gas in the 50s.
Mm-hmm.
Couple things on this, guys. If you come across a system like this, you'd have to make some major changes to this system if you went with the high efficient boiler, okay? Mike and I have both taken a lot of these old gravity systems and put in high efficient boilers, okay? When we do that, you have to be very careful in how you do a lot of different things. Like Mike said, you have an open expansion tank there at the top, okay? If you put pressure on that system and it's no longer open to atmosphere, then all of a sudden, you're gonna be boiling water out of the top of that expansion tank.
Making it rain.
It will flood.
I've got
the attic,
those
it'll
calls.
drop right down. Yeah, we both have had that.
Hey!
Yeah. And so not only that, guys, but also the other thing too is, like Mike said, you have very, very large pipes in this system, right? In our hydronic system, we want to have a bit of turbulence of water through that piping, okay? Through an old pipe system like this, where you have big pipes like this, what's going to end up happening is the water velocity inside that pipe is not going to be uniform. You're going to have a higher velocity in the center, but on the exterior of the pipe, you're going to have a lower water velocity. And you're not going to transfer that heat to the system as efficiently, okay? So pump sizing is very, very crucial in systems like this. You want to generate a more turbulent flow through that system. So you can't just apply general hydronics, rules of thumb to systems like this and expect it to work. My strong suggestion, if you guys come across a system like this and you want to, get this back into the 2000s here, right? I would strongly encourage you to call Mike Whitehead or myself, because there's some very detailed information that you're going to have to make sure that you hit on, and there's a little bit of work and knowledge to doing that. It's not common you come across these, and it's very crucial that you get some of those key components implemented into that new system.
Right, water quality, as this gentleman back there was discussing, a system like this, you got all that open contaminated water in this gigantic pipe with oversized everything.
Yeah, that,
It's just a mess. It's a minefield for just contamination, corrosion. So when you would bid a job, like we would be helping you not only select a filtration type system or device and kind of get you heads up on that, so you understand what that entails, and telling you this is gonna require a lot of flushing. You're not going there praying that there's a couple isolation valves, you can shut it off, cut the thing out, put the new thing in, open the valves up and run out the door, okay? Go ahead.
So you're saying you put a high efficiency boiler on those? It could-
You potentially could,
You leave it
not
open?
saying I would recommend it on everyone, no.
But you don't leave it open to atmosphere?
No, you're gonna close this off, cap that, you're gonna put a different type of,
I mean, with all that headache, don't you just tell the customer, look, you gotta get new pipes?
no, not if you can spend 4 hours and clean them out and get the right components on it to make that.
But like with the radiators and stuff, you're gonna put that pressure to it now. I mean, aren't you getting all the leaks?
Say, we're not gonna be putting much more pressure on it than, it's still low
It-
pressure.
yeah, it's still gonna be relatively close, I mean, well,
It could create more leaks, to your point, though, it's Pandora's box. Any type of system that was built in the, 1930s, 40s is going to be, or even earlier, some of these are probably earlier than that, I would say
yeah, I mean, just the,
20s or 30s.
just the weight of water alone is 0.43 PSI per foot, and we'll get into that later, okay? But if you look at this system right here, I mean, if you assume that expansion tank is up in the attic, right? And we got we'll call it a first, second, third floor,
Yeah.
we'll call it first, second, third floor here, okay? The highest water level that you have on your system down to the basement might be 40 feet, okay? If it's 40 feet, what is it
20
equal?
PSI.
20, 18 PSI maybe down at the boiler, right? You're gonna operate a closed boiler system on something like this at about probably 22, 24, so it's a little bit higher. So I don't, when you close off an open system like this to a pressurized system that's closed, yes, you're right, there are higher operating pressures and leaks could possibly appear that weren't there before. But that's more on going from steam systems to hot water systems, okay? That's more where that type of issues are gonna apply. One thing I wanna mention real quick on this too, guys, is these boilers are grossly oversized. Let's assume that this is a 2,000 square foot home, okay? You might have a 400,000 BTU boiler in here, okay? So sizing the new boiler, the properly sized boiler to this is also crucial. Don't take the BTU capacity of this boiler and just assume, well, hey, you know what, we had a 400,000 BTU boiler in here, that's what we need because that's what was in here. No, if you had a 2,000 square foot structure, you're probably only needing 100,000 BTUs, worst case scenario. So you just can't, take any assumptions from this system and apply it to the new system.
You know what you run into there, if it's a commercial space,
Say that again?
if it's a commercial space, and you now have to get the state involved.
Well, okay, so that's a good point. What do you,
Now you undersize that boiler, now you gotta get a design engineer in there, yeah.
so what he is suggesting is in a commercial space, if you downsize the heating, now this is state code, what it states is, if you downsize the BTU input capacity of any heating system by 15% or more, you have to get a state licensed engineer to sign off on the heat loss calculations, okay? Here at Johnstone, we have myself and 2 other guys that are state licensed engineers. So I can stamp and sign anything that you may need commercially for a new commercial project, or in this case, like he was suggesting, if you downsize that heating capacity by 15% or more, the state or the local municipality is gonna require to see heat loss calculation signed and stamped by a professional engineer. So I can do that for you guys, as well as a couple other people here at
You
Johnson.
can just do a site visit for that.
Yeah, most of the time we're out there to visit because especially in a system like this, adding up the installed radiation is very crucial as well. Okay, there's certainly a lot that goes into this. We're not hitting on all the points. We don't wanna overburden it with so much information. You guys forget everything we say too. But yeah, we would typically be out there. I have done a few heat loss calculations utilizing Google Earth and Street View and a couple back and forth questions here and there. But that's not as ideal either, so. And if you get into, if you have a commercial space on hydronics, this is a general rule of thumb, it doesn't apply necessarily to gravity systems here. But if you have a commercial building and you have a hydronic system, I would be very mindful of what they're doing with their outdoor air. Okay, the reason I say that is a lot of commercial spaces that have boiler systems in there have to have ventilation air. Okay, so we're drawing outdoor air into the space, and a lot of times there are hot water coils that preheat that outdoor air coming into the space. Okay, and then distribute it through the air handler system throughout the rest of the building. My point is, boiler size in commercial sometimes seem to be very large, but that's because they're handling a large outdoor ventilation load. I'm literally working on a project right now on the east side. It's a bar and a couple of rental spaces, and this boiler was so grossly oversized, the contractor thought, well, I'm just gonna downsize this, and I said, well, it's commercial, make sure you don't have any hot water coils preheating that outdoor air. And sure enough, later on he found it. We measured the airflow, and with some quick, easy calculations, we were able to determine that hot water coil was 80,000 BTUs just to preheat that outdoor air coming in. Okay? So that boiler was oversized by what appeared to be 100,000. Well, you better make sure that it's not just handling the envelope loss of the structure, but it's also handling the ventilation load as well. That's only gonna be for commercial though. So that's a general rule, certainly doesn't apply just to gravity. So.
Alright. So, that was a lot there, on our first slide. Alright, we do make site visits. We not only look at the building, but we look at the radiation, okay? And we're gonna try to help you guys focus on the two differences, okay? Because one is how many BTUs can the actual heater put out, like the radiator, or the amount of baseboard that you have, the fin tube. Then how much do you need, right? That's the other question. How much heat do you actually need in the space? So I want you guys to think on that, like that's important, even for forced air, for cooling. How many BTUs do I need to get into this room? Typically for forced air, you're like, how many 6-inch ducts do I need, or 8-inch ducts, right? Because you know how many CFM and how many BTUs that CFM carries. We're gonna talk to you about GPM. It's very similar to CFM and how it functions in our math and equations. BTUs are BTUs, that's the same. And then we still use a delta T, temperature difference, right? You guys are used to temperature differences, this is nothing new. So we're not gonna throw too much new at you. Mike already threw a weight of water at you for some reason. Well, for the height of the, so anyway, you know, this is not, don't be intimidated, that's my whole point. You know, but I don't want you to think that this stuff is that intimidating. You do it all the time. We're just going to make you think a different way. You know, our ductwork in this class is pipe size, is pipe. Whether it's copper, black iron, PEX, we're gonna use lots of different material, but just like when you're using different types of ductwork, it has different characteristics, right? Different restrictions, our friction losses is what I'm going for there. Flex duct, a lot less CFM than a smooth hard duct, right? All right. So, single pipe series system. These systems, you may see them out there, but they have their downfalls. This pump, for one, has to be sized to push the flow through every bit of radiation. okay? It's not paralleled off, it's gotta push from start to finish all the way around. So if we leave out of this unit at 180 degrees, let's say, we start to drop temperature. By the time it gets to this side over here, can everybody see that? By the time it gets to this side over here, we're not getting 180 degrees anymore, right? So this side of the house or building is gonna be hotter naturally just by the way it's designed than the other side. Unless there was a lot less radiation on that side and you start to add more radiation based on the water temp you think you're gonna get. Now, if the system went in this simple, I doubt there was that much math that was included in putting it together to figure out what you needed there. So, with these systems, no zoning capabilities whatsoever, unless you throw a towel over the baseboard or whatever, you know, like try to block it somehow without shutting the flow off, because as soon as you restrict the flow on any one of these, it affects the whole system. Everybody see that? No way to balance anything. So these systems can be noisy. You're gonna have that temperature swing, very, very ineffective type of way to do it. You may see a cabin or something like this, a small loft designed like this, but typically what you'll see is like an apartment zoned off like this, off of the main, right? You'll have a zone valve off of here, and then this thing swoops into that apartment, takes care of all that baseboard in that apartment, goes back to the return. So you can have series parallel type systems as well, just like electrical stuff. We just build onto these. So anybody see these type systems out there? Yeah?
You said usually the first radiator is the smaller one.
Right.
Usually.
Yeah, hopefully.
Hopefully. I had to put one in myself, I would duplex. I got questions about that one later.
So, now, some folks can get this confused with another system that's one pipe that I'm gonna show you next. Any questions on this guy?
Can I just expand on one thought there?
Yeah.
So,
Do you want the con?
sure, we'll do that.
I gotta grab something.
What's your name?
Okay.
Sorry.
How's it?
Well, I didn't catch your name.
My name's Nick.
So what Nick was suggesting is, in a system like this, the first amount of radiation typically would have less feet than the later parts. The reason he's suggesting that is because as we lose water temperature throughout the system, the amount of BTUs that we're going to emit through this baseboard per foot is less. So with the hotter water temperature, we might emit, let's say, 560 BTUs per foot through this radiation. But as we travel down and our water temperature drops, let's say we're only at 160 degree entry water temperature, instead of achieving 560 BTUs per foot, we might only be achieving 540. And as you go down further, here, at the very end, you might only have 140 degree water coming into this piece of baseboard. And if that's the case, you only have 300 BTUs per foot, okay? So the idea, of course, is you have less radiation here and larger amounts of radiation here, even if the room sizes were equal. So, I just wanted to expand on that. You want me to, I'll keep rolling with this one. So, this is another type of system that we see here. This is very, it looks somewhat similar to what we previously saw. We still have one pump on the system, and we still have one main system loop here, okay? The only difference that we have here is all of our radiation is teed off of the system. So this would be our supply line going out to the radiation, our return line coming back, and so forth. Supply line going out, return line coming back. Now, in regards to, yeah, pass, perfect. So what, real quick, I'll pick up on that thought. What Mike is passing around is what's called monoflow tees. There's two different styles here.
And I brought both.
He brought both.
So pass these along.
These are both tees that you're gonna find out in the field. One is cast iron, one is copper. There are a couple other styles, but what you're gonna notice is the tees look a little different. I mean, the cast iron tee is not a standard or typical tee, it's much larger. What you'll notice on the copper tee is you're gonna notice a painted ring. In this case, we have a red ring. That's a monoflow tee that's manufactured by Bell and Gossett.
We sell those and stock those.
Yeah, we have those in stock. You're not going to implement you're not gonna implement a monoflow tee on a new system, okay? You're gonna come across them on older systems. You're gonna find that sometimes they get plugged up, and you need to replace them. So that's why we have them, but they're certainly not gonna be used on new systems. Now,
The big one is though, you go in, they wanna do an addition, right? Or somebody has done an addition. And you go in and you're like, oh, this is a monoflow T system, cause Mike's told me about all this, that we seen it in the class. And then you go over to where they put that nice little kick space heater on there, or, you know, the baseboard in the kitchen that they remodeled. And guess what? It's a basic ass T. It's not one of these. And what? It doesn't work, right? We can't get flow through that loop. Why? It's not the same. It's not a T like what has been installed throughout that whole system. And then you'll see that, you know, you have to kind of be a detective on these jobs that you go to figure out what everybody else has done before you, so you know what to do or not to do.
so the way that monoflow T systems work, guys, if you remember this one extremely simple rule, like air and electricity, water follows a path of least resistance, okay? So what you're seeing in these T's as it's being passed by is something very similar to this, okay? So we have this small tongue here, okay? Now some people like to say that as the water is flowing across this tongue, it's being scooped and pushed up into the convector and back out, okay? It's actually not what's happening. What this tongue is doing is it's adding pressure drop, okay? We're adding what's called feet of head, and we'll get into that later. Resistance. You're adding resistance across this T. So what we are saying is water follows the path of least resistance. So if you did not have a monoflow T, most of the water is going to bypass your radiator up top, right? Okay. So every one of these T's here, for illustration, is a monoflow T. So if the water is coming down this loop, the water can go one of two ways. It can go up into this piece of baseboard, or it can bypass it and continue down the system loop. If we put in a piece of resistance here with this tongue, okay, what it says is, you know what, I have 5 feet of pressure drop if I go across this T and down out to the system. However, because we have this tongue, this monoflow T here, what happens is we may be creating 5 feet of pressure drop, okay, so now they're equal, so now some of your flow is going to go up into the baseboard, and some of the flow is going to bypass the baseboard. So that's how we are diverting flow into the radiation, because as soon as the water leaves this pump, all it wants to do is get back to this pump as fast as possible. What's that? Yeah.
So basically, one branches off into the radiator and the baseboard, and the other one just continues through the loop.
Yes.
Okay.
Yes. And on the copper one, it's very easy to see. There's a red ring. Okay. That red ring indicates what orientation that T needs to be in. Okay.
Are they different, like the supply and the return?
Yeah.
Well, yeah. So you can have monoflow, and I've seen them all sorts of ways. Monoflow T, as you're seeing, is it's not adjustable pressure drop across the T. You can't increase or decrease the pressure drop. The pressure drop across this T is what it is. You can't change it, okay? So, the question is, you know, and I think I'm getting your question here. If I'm not, let me know. Where do you put this monoflow T? Do you put it on the supply riser? Do you put it on the return riser? That actually would be a calculated choice. You can have it on just the supply riser. You can have it just on the return, or you can have it on both. You know, if you have a high pressure drop across your baseboard here, you're more likely to require 2 monoflow T's, one on the return and one on the supply. So the higher the pressure drop across here, the more likely you'll have 2 monoflow T's. Is that
Yeah, I've ran into one house where I saw the monoflow piece, she wanted to add the Ethan Morris type thing to the back vestibule addition to the house.
Yeah, little kick space
One-
heater.
one room, right? I says, well, I gotta do this primary secondary now, right, I gotta add 2 pumps to your system to isolate the monoflow system from your new addition, and she didn't like that, she
Yeah.
didn't like my friends.
You could have done this, where they wanted to add that kick space heater, let's just call this a kick space heater over here. I don't know. You could have just put 2 closely spaced T's here with the pump. The flow would always just keep going through there, or let's say it's coming this way. So if the flow's coming this way, it would circulate it.
So I could have just added one.
2 T's right there on that
One
main,
pump.
regular T's, regular
Yeah.
T's, yep. You could have added 2 regular T's close to each other, and then a circulator,
And then that would have been probably on the supply end of the boiler then, right?
yeah.
Instead of,
Yeah,
You could,
because if I'm having a thermostat, right, and a pump relay, right? I don't want the
Yeah.
return side.
or you
of the
could
pump.
get one of our little Taco pumps that has the relay built onto it, so you just hook your thermostat straight to the pump and it plugs in.
so the
Those
example,
are the quick, easy adders, you can smack in.
It's like 20.
That's what we're here for, we're here to plant seeds and add, that idea, a little different way to think about this stuff, so.
the example that he was illustrating real quick, guys, is the monoflow, if you have a monoflow T system, you had a small addition or a kitchen remodel, and you had to take out a piece of radiation that had the monoflow T's in it, how do we get flow to this new piece of baseboard or this new kick space heater? And like Mike was saying, we can do that without adding monoflow T's by doing different piping strategies and implementing circulating pumps. So don't feel like you have to keep the same style system, throughout the space. So, in a system like this, real quick, guys, I had mentioned about the temperature drop across the system loop. We kind of have the same effect, but not to the same capacity. In this previous slide, we have all sorts of temperature drop and a dropping water temperature as we get back to the boiler. In this system, we do have some temperature drop, but it's not as high as in the previous. Because part of this, right, if we have 180 degrees going out of our boiler and into this T, let's say we send 2 gallons per minute up into this piece of baseboard, we might be bypassing 8 gallons per minute. So as we are sending 2 gallons per minute of, let's say, 160 degrees down into this return line, we're mixing with 180 degrees at 2 gallons per minute. So we're not gonna be sending 160 out to this big piece of baseboard. What we're gonna be sending is more like 178 or 175 degrees into this line. So our temperature drop as we go across a system like this is gonna be less. So just,
Would you say that that's better than a series one?
oh, absolutely, absolutely, yes, for sure, for sure. Any questions on this system? You have anything to add, Mike?
Only thing I could add to that is I see them a lot still in churches, a lot of churches out there. Big ranch style houses you'll see sometimes. I've seen a few out in Union Grove.
You're gonna find them in structures prior to 1950.
Just looking at the way that lays out, as somebody that would think about, how would I put that in versus something else, and that's pretty easy looking, right? That's, you're wrapping the perimeter with your big pipe, and then you got some T's to go to all your radiators. It doesn't look that hard, right? There's not a lot of extra stuff there, so something like that was pretty appealing to some contractors because of how simple it was, how quickly they could put it in. But yeah, there's it's losing some of the appeal of what hydronics really can do too, which is lots of multi-purpose stuff like Mike was talking about, multiple zones. So not really utilizing, you know, a lot of the more comfort features and stuff like that, or efficiency features.
One other thing I wanna add to this system, guys, is this system right here is gonna have a much higher pressure drop than, let's say, this system, okay? Assuming that all the piping is sized correctly. This system right here is gonna have a higher pressure drop, because we have all of the monoflow T's adding resistance. My point though here, guys, is this circulating pump right here, you still have to be very mindful of making sure that this pump is large enough to flow water across all of these circuits, so. You wanna roll with this one, or? No? So this right here, guys, this is much more common. This is something that you'll see out there today. These type of systems get installed now. What we're illustrating here is we have a single cast iron boiler, okay? We have our supply pipe going up and out. We have one circulating pump here, and then we're supplying water out to our system. We're bringing water back in and coming back into the boiler here. Now, we're gonna get into a thing called closely spaced T's, hydraulic separation, okay? Some guys will say, well, I have a T here and a T here. I have closely spaced T's, and that's my hydraulic separation. That's not true. The orientation of these T's does not allow for primary, secondary, or hydraulic separation. Instead, what this is this is a bypass valve, okay? And what we are doing here is we are actually taking some of the supply water coming out of the boiler and actually bypassing the system, and we're sending it from this right T to the left T to precondition this return water coming back to the boiler. Now, this is a cast iron boiler. Does anyone have any idea why we would want to send supply water into our return line on a cast iron boiler?
You don't want the condensate.
Yeah,
No condensate,
There's
no
two reasons,
shock,
yep.
yeah, that's
both are correct. We don't wanna shock that boiler, and we don't wanna have condensate on that boiler, okay? Thermally shocking a cast iron boiler, if you have a cast iron skillet at home, you get it blazing hot, you drop water on there, what happens? That water flashes to steam, and it pops off the cast iron, right? That's exactly what we could potentially be doing in a system similar to this. So how do we get that kind of cold water on a hot cast iron system like this, right? A lot of times you could be coming from a night setback, you know, if that water temperature, sometimes this water coming back could be as cool as 65 degrees or so, okay? And if you bring that onto a hot cast iron heat exchanger, you're gonna be shocking that water for sure. There are some other issues with fill valves and things like that, but we won't go down that road for right now. The other thing that was mentioned, and I'd say probably most importantly, is we want to prevent condensation from occurring on this heat exchanger, okay? High efficient boilers condense, they have condensation. That condensation comes from the release of latent heat, okay? During the combustion process, the rule of thumb, there's certainly varying conditions to this, but when you have combustion take place, the dew point temperature of that combustion is approximately 150 degrees, okay? If your return water temperature is at 140 degrees or less, we're gonna have condensation form.
Is that pretty much true across the board, 140?
Yeah.
On any
Yep.
system?
Yep,
So we wanna balance that bypass in a cold system.
yeah, we'll get,
140 degree return water.
yeah, yeah, exactly. So, this condensation that's occurring is happening because our return water temperature is at 140 degrees or less. Now, on a high efficient boiler, okay, we have a combustion taking place, and we could be bringing back 100-degree water temperature, and we have all sorts of condensation. But that condensation in a high efficient boiler is occurring on stainless steel. Stainless steel allows for this condensation. Cast iron does not. Now, why doesn't it? It's because condensation has a very low acidic value. has a very low pH, I'm sorry, very high acidic value. It's a very high acidic value, very low pH, okay? And if you have any kind of acidic nature of the water or the condensation on this cast iron boiler, you're gonna eat that cast iron away. You're gonna ruin the heat exchanger from the outside in, okay? High efficient boilers, that condensation is accepted. It's
Usually.
acceptable, you can do that.
Usually, you'll start to see signs when you walk in and meet that boiler for the first time. You're like, hey, don't give me, a pain in the ass today, please. I wanna get home. But you'll see, right around the base of this, you'll see rust. You'll see discoloration, corrosion, and maybe it's coming out of the first couple joints. It's starting to grow stuff out of there. That's a sign. Ding! We got too low water temp coming back because the unit's condensing. It's gonna start condensing right away in this chimney because our flue gases are directly reflected based on the return water temp into the unit. The hotter the water is, the hotter the flue gases are gonna be. So, if we're starting to cool off, it's gonna start raining from the chimney down into the heat exchanger, on top of the burners, and then boom, no more hot surface igniter. You're back. Change that out again for the third time this winter. Right? Anybody do that? Go back a couple times a year? And just start taking notes. Why, what's happening? What can cause it to rain inside there on those burners? What can create this stuff? And a lot of times it's forced by the homeowner because the temperature's too hot. They gotta open windows, or they're struggling with comfort, or they figured out lowering the temperature not only helps with comfort, it saves me money on my fuel bill. So then why, at this point, why wouldn't I wanna lower that water temp? You gotta be like, well, Mr. and Mrs. Homeowner, because it's killing your boiler. It's, I can't service it 3 times a year, in winter. You don't wanna pay for that either. So, in those cases, might be time to look at a high efficient application if you're trying to cut those temperatures down so much.
So to bring it full circle, that's why we put this bypass in there, okay? Because we want to make sure that our return water temperature is 140 degrees or higher. That's going to prevent that condensation from occurring. One of the very first things I do when I'm on a job and I see a cast iron boiler in that room, the very first thing that I do is I look for a Tecmar boiler controller, okay? Tecmar boiler controller right there, the blue box.
Maybe a little white one.
Could be white, the newer ones are white. But if you have a cast iron boiler, the blue box is what I look for. Anyone know what the Tecmar boiler controller does, or why I look for that?
Outdoor temperature reset.
Yeah, I'm worried about outdoor temperature reset, okay? And what outdoor temperature reset does, or outdoor reset curve, is what we are doing is as the outdoor air temperature drops, we are going to lower our supply water temperature out to the building. What's up?
Raise.
Oh, I'm sorry, I did that backwards.
Outdoor temp drops, we raise supply temp, and as it warms up outside, we're going to lower the supply temp.
So what we're trying to do is save on energy, right? If we can supply the building with 130 degree water and still heat the space, that's good. That's good for the property owner. They're gonna use less gas, less energy to get the water from 130 to 180, okay? So a lot of times what you'll find is previous contractors will be in that mechanical room and they'll tell the property owner, hey, you know what, Mr. Property Owner, I can save you a lot of money. Let me put on this really cool Tecmar controller. We'll monitor the outdoor air temperature and we'll adjust our supply water temperature going to your building, saving you money. But what they didn't realize is this condensation, the low pH, or the low pH and the high acidic values to it, okay? And what they did is they actually shortened the life expectancy of that boiler from about, let's say, 20, 25 years to maybe in some cases 5 years or less. So the first thing I look for, guys, is I look for that Tecmar boiler reset controller in any cast iron boiler. Unfortunately, I probably find it 30 to 50% of the time. I find it way more often than I should, so.
But you can set the curve to be very limited. So let's say, you know, I don't want it to even get close to 140 degrees. I could set it to run from 150 to 185 degrees. You know, never letting that target temp get that low. So they're adjustable, you just gotta know what you're doing. Don't oversell something. We're teaching you, there are limitations to this stuff, and yes, we can save you money, Mr. Building Owner, but it's gonna be a short life for these guys, you know, these boilers over here. If you're looking to replace them in 5 years, I got a great plan for you. We start budgeting now. All the money I'll save you the next 4 years, and fuel, maybe we can come up with some extra for the new boilers, because you're gonna need them. But how are you gonna plan for the servicing to keep them running those 4 years with these low temps? That's the bugaboo. We have three-way valves, we have circulators that do boiler protection. Okay, so you get into a system where you're like, yeah, we cannot run this system that hot, period. I don't care if it kills the boilers, give me some new boilers. You could be a hero by saying, well, how about this? We keep these boilers, we protect the boiler water temp, and we lower the system temp down at the same time, without having to get high efficient new boilers. That's appealing. So you can do that. So like this circulator right here, it comes with temperature sensors. It has a boiler protection mode. You can run that in place of that bypass, in essence, and enable it with the other pump. So anytime it comes on, it's going to flow based on what temperature it sees on that return, and make sure it stays at 140 or 50 degrees, whatever you set it to.
Well, it's basically now your valve.
It's your valve, it's your bypass, so it's a smart one though. Nobody's gonna stay here, buy this boiler, and wait for them to bring that thing out of setback.
You still need a,
You're like, hey, what time are you getting up in the morning? Oh, I get up about 5. Okay, that means that, can you let me in around 4 so I can get that valve open all the way up? No. Once you leave that valve where it's at, who's gonna mess with it? Other than their grandkids when they come over and play trucks down there by. You gotta go back and figure out why the system has no flow. Well, Tommy opened that valve all the way up, and now it's just, you know, all the flow takes path least resistance. Here we are. But anyway, there are devices, thermostatic mixing valves that operate with no electric that you can put on there in place of that. So they're not cheap, but it's an end to a means here. We can we know what the issue is with killing the boiler or overheating the temperature in the building. We can fix it. What do you want to do? We want to add valves, we want to add pump, we want to add a whole new system. Or maybe we just start taking radiation out. Whatever's easier, right? Whatever the plan is.
The last thing I want to mention right here, guys, is notice that we have a valve on this bypass here, okay, like Mike was saying. This valve really should only be a gate valve, okay? I see a lot of ball valves in these positions. A ball valve is not a balancing valve, okay? A gate valve can be used to balance, but not a ball valve, okay? Everyone know the difference between a ball valve and gate valve? Well, real quick, a ball valve, guys, is a quarter turn. You got the handle, if my pipe is running vertical and the handle is sticking out this way, we're in a closed position. If I turn this 90 degrees clockwise, now I'm in an open position. That's the full movement of that valve from closed to open, okay? A gate valve is similar to a sprinkler spigot, where you have that round handle on it and you twist it, and you have to twist it maybe 10, 15 times before you finally get it closed, okay? That's a gate valve. Gate valves are used for balancing, okay? That's what should be on here, okay? And the reason being is when you're starting this boiler up, you're gonna monitor your return water temperature, and when you're doing so, you're gonna wanna make sure it's at 140 and higher by adjusting this valve, which of course allows a certain percentage of water to bypass your system, okay? Does that make sense to everyone?
But you need to let it run for a good 10, 15 minutes if you can, and let that system stabilize before you really make any final determinations with that.
I've seen a boiler, like you mentioned, cast iron, I went to type R control, if that is causing the return water to be too low. The only reason I mentioned this is I've seen it in the back of this house, when from noise, boiler just popping and banging, like I'm sure there's minerals in there or whatever. Can that contribute to mineral buildup?
No, water temperature wouldn't have anything to do with that. It sounds like you're dealing with an issue called percolation.
No flow.
Or no flow, you could be, yeah, you could be, so, it could be a lot of things, it could be water quality,
Lots of sediment.
percolating, it could be having not enough flow through your boiler and you're actually flashing the steam in certain parts of that heat exchanger.
I'm sure that shit has iron pipe everywhere, I'm sure there's a bunch of shit that heat exchanger.
Yeah.
Does it have an air eliminator on it?
It should.
Does it have a compression style expansion tank, or is
It's
it a
got the
ladder
old
or diaphragm?
compression, yeah, it's not.
So, we're gonna talk about that, we're gonna beat that horse here in a minute. So, this is pretty typical, guys, any questions on this? We talk about some components here, while we got this nice little diagram. System circulator on this guy, I get this question probably 2-3 times a week, Mike, where do I put this pump? Where you wanna put it, is what I don't have an opinion when I get up in the morning, you know, your system, your situation dictates what you should probably do. I don't know. Until you send me pictures, I can't really start making a, you know, even a qualified opinion, because still it can go on either side is the right answer. But the trick to that whole thing is, you see this? This is the point of no pressure change, where your expansion tank and your fill valve key into this system. And that's on the suction side of this pump. That pump is pumping away from that, right on the back side there. So with this being in place on the back side, the suction side of the pump is actually able to do its job. Okay? It's actually able to be a pressure differential device. It can create a pressure differential at that point, because we're maintaining pressure here to give it the ability to create a positive side on the other side. So always be pumping away from this. Now, could you put the air separator over here and the pump right here? Yep. But if you put the pump down here and then that right there, you're essentially pumping right into that expansion tank, making that pump less effective. It's struggling to even do its job, so your system's now in limp mode. It works except for when it gets cold outside mode. Okay? Is that what we're trying to sell our customers? No, we don't want that to happen. So when that pump takes off, you should see that your temperature difference is around 20 degrees. Okay, 20 to 30 degrees, you know you're in the pocket. That's what we're designing for. Okay, 20 to 30 degrees, I would say, is a good range from your supply to your return to know, hey, when I'm heating on a design day, I've got that temperature difference, I know I got good flow. I know what's happening. If that flow is 60 degrees different, 70 degrees different, do I have flow? We're in limp mode. I might have a half a gallon a minute, maybe a quarter gallon a minute. So yeah, I technically, as my teenager would tell me, yeah, I have flow. But is it enough to do the job? No, we're trying to get 12 and we got a quarter, you know what I mean? So it's not applicable. So that's how we use that temperature difference to know, hey, you know, something's going on here, I don't have flow. Let's talk about parallel system here. These are more common. It's kind of like this too, right? It's a parallel, two-pipe parallel system. We have a supply and return going out. So similar situation. We're just kind of showing you the overview of that system at this point. The most important thing on this system is right here. All of these balancing valves. That little square there is a symbol for a balancing valve. Now, why is a balancing valve important? Anybody know? If they weren't there, what would happen? Could anybody describe what this guy would be feeling over here if there were no balancing valves on that loop anywhere? It'd be colder.
You got first out, first back there.
First, for what he's saying is first out, first on the supply, first radiator here is the first one to go right back. So, if that was a system that was put in, seems fairly easy enough to do. People do this kind of install all the time. They don't always work because we forget some things. So first in, first out, the path to get back home for that pump, like Mike said, all it's trying to do is get the flow back to it. That's all it cares about. So if it can take the shortcut right here, who cares about down here? It doesn't ever even think about going that far. It may have enough to get this guy a little, or even this guy, but nothing out there on the end. So you have to put these flow valves in here, balancing valves. Here's an example of one right here. This is a quick setter. Caleffi makes it. You pull the pin and you adjust this. You got a BB in here that tells you how many gallons a minute you're setting it at. Once you get to where you want it, you let go of the pin. Now you've balanced that zone. Also, these are also balancing valves, okay? There's flow meter, but it's also, you're able to adjust this flow meter. And so each loop, I can send different flow to it. Everybody see that? So whether it's a system with quick setters, or even just a standard gate valve or globe valve that Mike was talking about, one of those long-winded jobs that you gotta keep turning forever, those are effective too. They're not as cool as this with indicating what I've got for flow, so you'd have to put temperature gauges on that zone with a globe valve and stay there for a little bit, dial that thing in, okay? Now I've got about a 20-degree temperature difference, I'm good. I can move on to the next. But the balancing valves on this guy is the most important thing. You got a pump on here, one pump. Now, if this was zone pumps on here, let's just, maybe I don't want to go that far yet. We'll get into that. So we'll talk a little bit more about that, but some systems get converted from zone pumps to zone valves. And I'm okay with that. It's actually the most electrically efficient system you could probably operate with. But there's some booby traps that you can get into because you didn't have these with all the zone pumps zones. You didn't have balancing valves on those. So then you smack zone valves on there, and now guess what? It's a free-for-all. All those zones open, its flow's just going to take the path of least resistance. So the shortest zone hopefully satisfies quickly, so we can get the show on the road, get the flow out to the other longer zones. And it's going to go in order. The shortest zone is going to satisfy first, then the next shortest, then the next. So sorry for you if you're on the second floor in that house. Put grandma down in the basement, that's where she's gonna stay the warmest. She can't be up there no more. Otherwise, we gotta add some zone, or some bouncing valves to that quote to get you what you need. So you can go to each zone, bang, 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 each one gets its own flow. Or maybe you run it off of a manifold. Any questions on that? It's a pretty typical system there. Now, reverse return. So, we look at this. This is coming out. The first one that it goes to is actually the last one to go into the return to come back to the boiler. Everybody see that? And on here, they saved some money. They used about the same amount of piping, but they saved on 6 balancing valves. Balancing valves, as cool as this thing is, it's not free. You gotta build that into your package, right? So, some systems were designed this way, if you're lucky. Not many, residential were done this way, I'll tell you that. But commercial, like commercial stuff, you'll find they actually had to do it this way because an engineer forced them to. Right? So, I've met those engineers. So, like, no, you're gonna do it this way.
I'm going to a 7-story building.
I can't, I don't have the time to be on the phone with you explaining why this doesn't work if you don't just pipe it this way. So, no balancing valves, they're not necessary. The first one in is the last one to go, so each set of radiators here, it's the same amount of work for the flow to get through each one. Everybody agree with that? Self-balancing. Ooh la la. So, when we do multiple boilers together, like cast iron boilers, and we're just doing system primary flow through it, I like running the system piping reverse return through those boilers so that you all get the same flow, equal flow and stuff. Pretty basic. Now, here's what we get into when the high efficient air came out. We decided that we needed to do primary, secondary. The terminology gets thrown around all over the place. Primary, secondary piping. Now we have 2 circulators on the system at a minimum. We've got a boiler loop and we have a system loop. Typically call this the primary loop, and the boiler loop is the secondary loop. So the primary, secondary. Boiler, if you want, it could be the most technical thing, is the boiler loop. I don't care. I don't get mixed up in the terminology as much as I do, what's doing what here. This loop is connected to the boiler, so it's easy to just call it the boiler loop. Now, we've got closely spaced T's tying in our boiler loop. Now, what is going on with these T's? These are on the branch side of the T. Everybody agree? The boiler loop is teeing into the branch port on the T. Everybody know what the branch port of the T is? So, if I've got my primary pipe coming through this way, and I'm going to put a T on it, this part is the branch. So, if you have, let's say, a 1 1/4, this is 1 1/4 by 1 1/4 by 1. Okay, so this would be 1 1/4. This side of the T is 1 1/4. This branch is 1 inch. Everybody tracking that? So if you ever need to order a tee from anybody, that's the way it is, okay, the description. 1 1/4 by 1 1/4 by 1, 1 1/4 by 1 1/4 by 1. If that was a 3/4, this would be 3/4. You get that? But you cannot tie your loops together with different parts of the tee. So both of these tees have to be on the branch going to the boiler. You cannot turn it to be like this.
Let's,
What are the conditions that are required, that make it necessary to have primary and secondary? Why would we want that?
Good question. So, what we were talking about in a lot of those older systems are bigger cast iron boilers. They hold a lot of water, a lot of volume in those systems. We're switching over to boilers now, high efficient boilers in a lot of cases where the volume in this heat exchanger is now under 2 gallons. We may go from a 30-gallon volume heat exchanger to under 2 gallons of water. Now, this boiler is very particular about a minimum flow rate. It doesn't want to see under a certain flow rate and doesn't want to see over a certain flow rate. So, based on what your system requirements are, that could change. You could have 10 zones out here on zone valves. And one of those zones could heat just a 6-foot piece of baseboard, right? It could heat a 5x5 closet, for all you know. It could be a towel bar warmer. You don't know, so if that zone is capable of bringing on just one zone, bringing on the boiler as a call for heat, to heat up that towel bar warmer, you're going to fire up this 200,000 BTU boiler for a towel bar warmer. The towel bar warmer gets a 1/2 gallon a minute. This thing needs 4 gallons a minute at minimum. That's why we have to have 2 separate loops. Because if the system flow tanks out, or just by design, it can run that low, this thing will never see 1/2 gallon a minute. It's always going to have its own flow here based on its circulator in this loop. It's unencumbered by what's happening out here, and we're going to talk about that. But that's why we have to have it. These things can't slow down fast enough. If that system were to go down to 1/2 gallon a minute, and it was just full flow through here, before it's going to blow the relief. Because it's just, that's going to happen very quickly. This is just an 85,000, but if it was 200,000, it could be more serious. The bigger, more BTUs you have into these things, the faster it can happen. So, we'll show you one of the install manuals. There are minimums and maximum flow rates to these heat exchangers. And so, the main way to absolutely ensure you're getting that is to do primary and secondary. What time is it?
9:20. You want me to do the?
You got it on the back
Yeah,
side?
I got it on the back. Right?
Yeah, we can get to it.
Yeah, that's fine.
Mike's getting excited. Not only he's getting to do some math and some nerd stuff here, but this is a thermal image of those closely spaced tees, okay? So, in this image, what we're showing is that the flow rates of the system and the boiler match. Everybody see that? They have to because there's no flow here. If I got 10 gallons a minute here, and let's say I only had 5 here, I would have 5 gallons a minute blowing past, right? Because if I got 10 gallons a minute and only 5 going through here, So anyway, this is a thermal image, like I said, kind of showing you what's happening between the T's when the flows match. Now Mike, take it away.
Alright.
He's gonna show
So
you, oh, I locked the one wheel.
No, we're good. I was just gonna flip this on. That's correct. I'm sorry. Alright, so I think what, Lutz's question was, why do we have to do this primary and secondary? What it allows us to do is have different flow rates through our two different loops, okay? So as Mike was saying, as our system, this being the system, okay, this is our system loop, as the flow rates through our system change, we're gonna make sure that the flow rate through the boiler loop doesn't change. And we do that by utilizing hydraulic separation. One way to utilize hydraulic separation is with the proximity of these two T's being closely spaced. There are 3 rules of thumb as to the distance between these two T's. The first rule of thumb is you want these two T's to be no further than 12 inches on center from one another. Okay? The second rule of thumb is no more than 4 times pipe diameter. So if you had 2-inch pipe here, that means that your two T's should be no further than 8 inches apart. The rule of thumb that I prefer is get these two T's as close together as possible. The closer together you get these T's, the less likely you'll have problems.
Close to the pro press will let you.
Yeah, yes, as close as the pro press will allow you to get. Okay. So to illustrate how we are able to maintain a specific flow rate through the boiler while having a variable flow through the system loop, it's best illustrated this way, in my opinion. So in this illustration, we have a 100,000 BTU boiler, okay? And applying some rules of thumb, that means that we're gonna need 10 gallons per minute through this boiler, okay? The reason we need 10 gallons per minute through this boiler is the factory has told us I need to maintain a very specific flow rate through myself, and you're gonna maintain that by this piping strategy. So we're gonna always have 10 gallons per minute across this 100,000 BTU boiler, okay? But what happens when you have a house that you have a lower level zone, a first floor zone, and a second floor zone, right? Your flow rates through your system can change. So if we only have one zone calling for heat, let's say this lower level is calling for heat, these two zones are off. Let's say that these two pumps are off, okay? These are not operating, so we just have 5 gallons per minute going out to our lower level, okay? That means we must have 5 gallons per minute coming back, okay? So we have 5 gallons per minute coming down our return line here, okay? Now we come to this T, and the water's gonna say, well, I can either send 10 gallons per minute down here, or I can try and push 5 gallons per minute out back to this pump, okay? So what's actually happening here is as we are sending, this pump is moving 10 gallons per minute, as we are sending 10 gallons through our boiler up the supply line, we can either go to the left or we can go to the right. If this pump is operating at 5 gallons per minute, what we're gonna do is we have 10 gallons coming up, we're gonna send 5 gallons per minute to the left out of this T, and we're actually gonna send 5 gallons per minute from this left T to this right T, okay? And the reason that that's gonna work this way, so we have 5 gallons per minute going to the left, we have 5 gallons per minute coming back, and this pump is requesting 10. So in between these two T's here, what we actually have is to get to 10 gallons per minute, is we actually are sending 5 gallons per minute from this left T to the right T, right? So now all of a sudden when we get to this T here, we have 5 coming back, we have, I'll say, 5 left over, so now we have 10 gallons per minute going through our boiler while we're still sending 5 gallons out to our system. Does that make sense? If it gets a little bit colder outside and the first floor calls for heat, now we have another 5 gallons per minute going out to our system, okay? So these values change here a bit. So we have 5 gallons per minute coming down this return, 5 gallons per minute coming down that return. So 5 coming plus another 5. We have 10 gallons per minute coming down our return line from right to left. Our boiler is pulling 10 gallons per minute out of the system loop down into here. And we're sending 10 gallons per minute up. And we have 5 and 5, so I'm sending 10 gallons per minute to the left. And I've actually created no flow across these two T's.
So that's what you got right
It's
there.
exactly what is illustrated up here, okay? It's the same thing. So what I'm saying is, when our flow rates are equal across our boiler loop, and our flow rates are equal from across our boiler loop and our system loop, we actually have no flow across these two T's. Gets a little bit colder out, the second floor calls for heat. We have 5 gallons per minute going to our second floor. So now we have 15 gallons per minute going out to our system. If we have 15 going out, we better have 15 coming back. And this pump is pulling 10 down. This pump, if this pump can only move 10 gallons per minute, you're not gonna pull 15 gallons per minute down here. What you're gonna do is you're actually gonna send 5 gallons per minute from this right T to the left T. So if we look at the boiler loop, we have 10 gallons per minute coming into the boiler, 10 gallons per minute going out, and we're actually sending all 10 gallons per minute out to our system loop, and 5 is bypassing our boiler. But what we've illustrated this entire time is as the flow rate through the system changes, what isn't changing? The flow rate through the boiler. In all of these conditions, we have maintained 10 gallons per minute across our boiler. And that's a wonderful thing when you have high efficient boilers, because the manufacturers state, I want a very specific flow rate. I want 10 gallons per minute through my boiler. So does that make sense to the closely spaced T's?
And the flow is important there, right? Through that T.
Yeah,
Yeah.
absolutely.
I've seen it before where, I guess you're calling it the primary loop.
Well, I would call it
System
boiler
is
loop and system.
flowing the other way, yeah.
Well, that's the next thing I'm gonna touch on here. So, one of the things that I get asked when I send out a pipe, so Mike and I we do piping diagrams for people all the time. So if you guys need a piping diagram, we'll make a piping diagram for you. And I will put together the piping diagram, as you see it here. And one of the questions I get sometimes when I send out a piping diagram from the contractor is they say, Mike, you made a mistake. I said, oh, I'm sorry to hear that. What did I do wrong? And they'll say, well, you have flow going in 2 different directions here, right? So if we look at the boiler loop, right, we have flow illustrated by these arrows. Okay? We have flow from this left T to the right T. And then they'll say, well, your system, you're flowing this way. You have flow going in both directions across this T. So they'll say, what they'll do sometimes is, if I'm lucky, they'll say you made a mistake, take a look at it. Or what they'll do is they'll take the liberty, and what they'll end up doing is they'll say, you know what, he just made a simple mistake, we're just gonna do this. Because in their mind, they think to themselves, well, now I have flow in the same direction across these 2 T's. That ain't gonna work. You will not maintain a proper flow rate through this boiler. All you have done is ensured that this pump runs in series with these pumps. That's all you've done. Your flow rate through this boiler by crossing these 2 T's is going to create a problem. So just be very mindful of that. Okay, it looks a little goofy on piping diagrams. It looks a little goofy when you're doing it, but that's the only way it's going to work. This will not work. Yeah.
So does that change the flow rate going into the boiler?
It does.
Okay.
It absolutely
So
does.
increasing it more than?
Increase. Well, it would increase it. Yes, it would increase it. Yeah, because this pump is running in series with these. We no longer have hydraulic separation. Our system loop is not decoupled from the boiler loop.
Yeah, this is a football bet.
Yeah. I mean, here's the deal, guys. One of the biggest struggles I come across is when I go into mechanical rooms, I see errors in the way that boilers were piped, okay? And one of the biggest struggles that you can come across is when you find errors in the hydronic system, right? You're gonna I'll tell the contractor, listen, this wasn't done right. This wasn't done the way it should have been.
He's like, say what? No.
And so what happens then, of course, is I point those issues out and I say, listen, if we change this boiler out, or we change these components out and we keep this as is, we might run into a problem. Then, of course, the homeowner's standing there and they'll say, well, I haven't had a problem in 20 years. They may not have. People can get away with some of the craziest things I've ever seen, and I don't know how that building is heated. You know, so that can be a bit of a struggle. If I see something like this, I'm gonna let you know and say, listen, this isn't acceptable. This isn't going to work. We can have an issue. So, someone had said, I believe, is it a guarantee that boiler's gonna fail if you pipe it like this? No, it's not.
What I typically see when they're like this is this boiler just short cycles. As it gets up to temperature, it's just sucking the hot water because the main system flow, at least 5 gallons a minute when it's all on, is going that way. So it's dumping hot water right back into itself. So it'll just turn on. It'll just on and off.
Any questions?
I just wanna make a point, that it's okay
Yeah.
for the pumps to be on the return side of the pumping the other direction.
It is. There's other system components that we have to be very mindful of, and we'll go deep into that after break.
When you have come across a job and you got a bunch of pumps on the return, that does make it difficult to locate that air separator and expansion tank. Typically, what I'm hoping that we can talk into is taking those old swing checks and flow checks out, relocating the pumps on the supply, because you're putting new pumps in hopefully anyway,
Yeah, I guess what's confusing.
and they have check valves in them, which is what the flow checks are doing on the supplies. But then you can hang your air separator here in your expansion tank, bring your fill in, have no issues with that.
How we get into all this, I'm sorry to jump in ahead, yeah, your air separation is on the hotter side of the system, right?
Yes,
If you can,
it's best located there.
yeah.
So if you do run into it where you, all right, so rule of thumb is to have the boiler pump on the return so that it doesn't run so hot, right?
Well, okay, that's a good point, guys. The question was, maybe not question, more or less statement. The pump is shown on the return line. Why is it on the return line? The reason I show this pump on the return line, guys, is, well, it's a couple reasons. A, you always want the pump to work on the positive side, right? So our pressure drop is this boiler, right? We might have 4 to 15 feet of pressure drop across this boiler, okay? We want that pump to work on the positive side of that pressure, okay? So whatever we're generating, we're discharging here. But most importantly, the biggest reason I will always show my pump on the return line is because so many of these high efficient boilers, and the high efficient boilers that we sell too, have pressure sensors in here, okay? If you put this pump on the supply line and you're pumping out of this boiler, I've seen it all the time. That pressure sensor will go into a hard lockout sometimes, right?
Usually it's 7 PSI, usually something like that.
Yes, so for example, we have a Navian in our arsenal, okay? The Navian goes into a hard lockout at 6 PSI. And I've seen it where we have everything piped exactly the way we need, but the pump was put on the supply line. When that pump turns on, we can create an artificially low pressure in that boiler, lower than 6 PSI, and the boiler goes into a hard lockout. So I always want to, in high efficient boilers, I always want to put the pump on the return line. Is it an absolute requirement? No. But are you going to save yourself some headaches on several jobs? Yeah, you will.
Just on the boiler loop though, right?
Just on the boiler loop, correct. Yeah, there's a whole other thing. We're going to get deeper into the system piping, why the pumps are on the supply. The pumps don't have to be on the supply. They don't have to be. They can be on the return. But like I was saying, we got to be very mindful of where we put some other system components to that as well. Yeah.
What I've noticed is most of them are integrating that pump into them. Right.
Oh, yeah, so a lot of high efficient
This gray
boilers.
one here that I took the lid off, it's got a pump in it, and it's just a boiler only.
I ran into guys where their backflow preventer, they can't figure out why they're changing it once a month. And they put a new boiler in there and they have that pump inside the boiler integrated. And then they also, from the old boiler, if it didn't have an integrated pump, wired that pump, so both pumps are on in series. And you gotta pay attention to the new stuff you're putting in, I guess.
Yeah, for sure. But there was a question you had earlier, yeah.
Is the closely spaced keys like the same thing as the hydro separator?
Yeah, and we'll get into that shortly here too.
Yep, that's right up. So if we're gonna keep moving on a little bit here. So remember when I was stressing to you that when I drew this was in remembrance of that, okay? So plumbers, they do real nice sweat joints. Look at how good these sweat joints are, guys. That's clean, baby. Those look good. But he struggled with having these both on the branch, right? So that's the branch. So ideally this would have been the boiler loop, and then the system was teeing in on the branch of these tees. Well, I guess he ran out of elbows or something to keep him from keeping this tee in the same orientation as this one, coming straight up through there and then back down. That would have kept him working great. But he tried to be lazy, in my opinion, and I told him that. He needed to cap that. That was not being used in the chimney anymore. So as part of his excuse was, well, the old vent pipe is in the way. I'm like, well, why didn't you cap it anyway? Why did you leave it in there? And then so he was out of excuses. I'm like, hey, you can't tell me you didn't have another 1-inch elbow to make the system work. And he's like, I bet you my paycheck. Let's. If I fix this the way you tell me to, you guarantee it's going to work. I'm like, yes. If you just done it the way I told you to in the first place, it would work, Jeremy. So anyway, what was happening was when this thing would call for domestic, there was a boiler and an indirect tank on there. Since we were not primary secondary correctly, we would force flow through, guess what? Every zone in the house. The living room was like 85 degrees. On a 40-degree day, guess what? Why? Because they kept using, like they were using a lot of hot water, and that was just pounding the ever-living crap out of the system. Instead of getting 140 degrees, it was getting 180 degrees. Whether it was calling for heat or not, didn't matter, because they were draining this water heater, so it just kept pounding the whole system. You're going to run into these issues. You're going to get that call. This zone heats without the pump on. Why? We can induce flow by doing silly stuff like this. We can make another pump that's not really supposed to have anything to do with that zone, have everything to do with that zone. And this is a real life example of that happening. It basically, that turn of that T created chaos. And the difference between the job making money and losing money. So, here's a couple more examples of the ability to do this without, having any guesswork involved, with making it super easy for you to connect this stuff. Hydraulic separators, or the manifolds, or even a buffer tank. So those are 3 other options that are point to point, hard to mess up, in other words, things you can do to create primary secondary. Navient's got a nice setup with the manifolds on the bottom of theirs. They've got the connections right here to connect an indirect tank if you so choose in the future. And put your boiler pump in there with isolation, as well as to do flushing. You can flush through those 2 ports, flush the internal side of that heat exchanger up. with the Hydrocep, you get some other options, or added benefits, I should say, value. You get air elimination added. You can get a dirt mag integrated with these things now, magnetic. You know, a lot of that black water, we talk about water quality towards the end a little more, but the black stuff in that water is magnetic. And we put these nice fancy ECM pumps in here with rare earth magnets. They just now become your system filter. So we want to put something else in there that's going to help collect that stuff out other than our pumps. Because even these pumps are magnetic motors in here, you know. They're not rare earth near as strong as the ECM motors. So you have a system with black gunk in the water. Let's talk about maybe adding something like this. It's something they need. That water quality is mission critical. It's running through everything. Just a little sidebar. If you guys were to take and buy a new truck and you say, and the dealership was like, perfect, I want to take your truck, your old one, around back before you pick up your new one because we got to drain all the fluids out of that old truck and put it in your new truck because it comes empty, it comes shipped dry. There's no transmission fluid, no antifreeze, no gear oil. I'm going to take all that stuff out of your old one and we're going to put it in there. Cool? Hell no, that's not cool. Well, that's what you're doing when you put in a new boiler into an old hydronic system. You keep all that fluid in there, and if it's contaminated, you're in for a mess. So we've got stuff we can add to the systems, whether it's chemicals and filtration devices, and sometimes you may need both for a while before you get that water quality settled down. But one of the biggest issues with water quality, since I'm still on that, is air. Air is a catalyst in these systems. A catalyst, guys, is basically a shit starter. Okay, it's the guy in the group that gets everybody riled up for no reason. Air gets in here, it takes all these dissimilar metals in the system, and it makes them want to fight each other. If it wasn't in there, they'd all be just relaxed and just kind of hanging out, you know, amongst each other. But with the air in there, it's creating a more of a chemical reaction and creating these dissimilar metals to go at it. And with that, you get the corrosion, you get the bad pH levels, you get all this nasty stuff in your water. Okay, so we want to teach you guys how to not only treat it but to prevent it. So we'll talk a little more about that. I think it's time for a break. We'll just rehash this when you guys